Hi friends, welcome to my channel. Let's continue on the problem related to linked list cycle. So this is today's daily challenge problem 142. So if you haven't checked out the previous video, that is a video for problem 141. So it's good to check out that video when we look at this one. So for this video, we're going to explain the Floyd's cycle detection algorithm, or slow fast pointer method in this context. First, I'll read through the problem statement quickly to digest the requirement, and then we explain the intuition and the extra things built from problem 141, and then we do the coding. So actually, as we understand the intuition as a mathematical analysis or reasoning, so writing the code is actually very straightforward, if not a piece of cake. So now let's look at the problem statement. So given the height of a linked list, return the node where the cycle begins. If there's no cycle, we're going to return null. So this is the problem statement. So here are three examples. So similar, the examples are like the ones in problem 141. So in example 3, so there's no cycle. And in example 2 and example 1, so there are cycles. So in example 1, the entry point of this cycle is node 2. And in example 2, the whole list is actually forms a big circle. So the entry point is the height node 1. So these are the constraints, like the number of nodes and the values of the nodes, and the position is -1 or a valid index in the linked list internally. So that's the problem statement and the examples and the additional assumptions or constraints. So as we know from the previous video, it's very easy to design or write code to determine if there is a cycle or not. But here the problem is one step further. So we want to find the entry point of this cycle. So still the intuition is the same, right? If there were a cycle in the singly linked list, then the slow and fast pointers would meet at some node in the cycle. So in other words, the fast pointer would catch up and pass the slow pointer in the cycle. So the intuition is very natural and easy to digest. However, here the question is how to find the entry point of the cycle. We need some extra but still easy reasoning. So here is an example. So I want to first identify the things and put the ideas into context with this simple example. So we have height and node 1, then connect to node 2, to node 3, to node 4, 5, 6, 7, 8. Then 8 connects to node 4. In other words, so this whole linked list contains a cycle, and the entry point or the beginning point of the cycle is at node 4, right? So we want to find this node 4, right? So this is what we want to do. So in the above example, as we mentioned, node 4 is what we want to find. So let's analyze how to get this node. So actually we can start two pointers. One is slow, let's start from node 1. Similarly, fast, start at node 1. And then we let the fast pointer move twice as fast as the slow pointer moves. Then these two pointers will meet at node 6. So for example, at the very beginning, so they are both at node 1. Then next step, so slow moves to node 2 and fast moves to node 3, right? Then next step, slow moves to node 3 and fast moves to node 5. And next step, slow to node 4 and fast to node 7. And then slow to node 5 and fast to node 4. And then slow and fast meet at node 6, right? So this is where they meet, right? As they meet, we know there must be a cycle. But here in this problem, we want to find this node. So here, let's introduce some symbol to analyze, right? Here, what we want to explain is the observation. So from where the slow and the fast meet, we can see if we move slow 3 steps further. So because they meet here, a slow moves 1 step, 2 steps, 3 steps. So we will arrive at the entry point 4. So similarly, if we start from the height, move 3 steps, 1, 2, 3, we also arrive at this entry point. So here we want to explain why, right? So let's assume that the steps from height to the entry of the cycle is key. So here 1 step, 2 step, 3 step. So let's use this as key. So in this example above, key is 3. And then the cycle length is capital L. So here 1, 2, 3, 4, 5. So in this example above, the L is 5. And then steps from entry point, the 2 pointers meet. So because they meet at node 6, so here I'll call this D, but in this example, the D is 1, 2, right? From the entry to the place where they meet, this is 2. So we introduce the K, L, and D. Then after time t, so when slow and fast meet, so slow moves like this, K plus D plus a certain number of rounds in the cycle, right? So the steps the fast pointer moves is doubled, right? Double the step is 2K plus 2D plus 2 times N times L. So in effect, so fast actually moves 1 cycle steps more than slow moves. So you can see this modulo L. So then I just use this one. So it equals the slow moves plus L. So you can, to be safe, you can mod in the sense of modulo L. Then we do the subtraction. So we're going to get K plus D equals L. Then we put D in the right. We get K equals L minus D, right? So in other words, so at the position where they meet, so then we move K steps. It's exactly here, right? Here, 3 steps equal this one from the beginning. Here, both are 3, right? Or in the sense of modulo the cycle length. So this way actually tells us how to get the entry point. We just need to move the height or slow L minus D steps further to get the entry point, right? So that's the whole idea. So here again, I'm going to first write this using the slow and fast pointer method, and then also I want to mention the brute force solution. So with that said, let's look at the coding part, right? So for the coding part, let me first write the one we want to explain, then we want to use brute force one. So first I'm going to use a slow, fast, and entry point. So not the entry. So let's use this maybe entry. So height. So here I would just want to, after we find slow and faster meet, then we just move certain steps. So what we are going to do is like this. So while fast and fast next, right? So this is our while loop conditions. And then what we are going to do is to move slow 1 step each time next. Because fast is not now, so slow must be not now. And also because fast next is not now, so we can do this. Fast equals fast next. The reason is that this guy is not now. So what we do here, so we want to check if slow equals fast. So this condition basically tells us there is a cycle and the slow and fast meet now. And then we want to move slow or height or the entry point, the K minus D step, right? So if you want to specify. So what we are going to do is that let's use a while loop to make this number of steps. So in this while loop, and the number of steps is not specified, but actually what they are doing is this, right? While slow does not equal to entry, right? Then what we are going to do is slow equals slow next, and entry equals entry next. So the entry at the very beginning is head, right? It's corresponding to like this. This one I'm going to move from node 1 to node 2. So here corresponding to slow moves from node 6 to node 7, and then node 2 to node 3. Here node 7 to node 8, then node 3 to node 4, node 8 to node 4. Then they meet. So it means that this guy is the entry point of the cycle, right? So that's the point here. So after we exit this while loop, then we just need to return either slow or entry, because after we exit while loop, the state is that slow equals entry. So let's use this one. So if after this while loop nothing has returned, so we just return, right? If you like, you can return null. So this short code actually forms a solution format to this specific problem. So before we do anything, let's first do a test. Oh yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So that's actually almost the end of this video. Basically, we analyzed the reasoning, or we explained how to get this entry point one step further after we detecting the existence of cycle. And then we write the code. Actually, the code is very short, but it contains a lot of a number of stuff. So now let's first make some annotation here, as for problem 141. So here is a slow fast pointer, right? So this space is O1, right? So space is O1. All right. So now let me copy this function signature, and let's write a brute force solution. So use a set, and the space is a problem because we store a node, and we are going to store all their descendants, right? So here I'm going to use a thin as a set. So and then we just iterate. So right. So let's use current equals height, and then we do the while loop, while current. Then we're going to check if current in thin. So if we thin this one, so we're going to return current in this problem rather than a boolean like in problem 141. Otherwise, so we're going to thin add this current, right? And then we're going to set current to be current next. So after the while loop, if nothing returns, so we're going to just return. So this is a brute force solution. Now let's do a check. Yeah. Yes, but in this, the problem for this way of solving this problem is that the space, right? We store a lot of nodes and their pointers. So let me change function signature. So this is the solution we will emphasize. This is a brute force, sort of brute force, I would say. I guess with that said, that's about it for this specific problem and this video. You are welcome to check out other videos in my channel. Thank you.